Alright, let's go through those few functions we haven't really finished in class, or not in detail at least. So I'm going to start again with the logarithmic function, and I'm going to go with the one that's f of x is equal to a log of x. Have you remember that this would imply I'm using a base 10 when you don't see a base written here as a subscript, right? Then it's a base 10, commonly known as the common logarithms. And if you have anything else but that, so for example, if I had any other number here, then that would be my base b. Okay. All right, so there are some conditions here, and the condition is that whatever that base is, b has to be greater than 0, meaning it has to be a positive number and it cannot be 0, and b cannot be 1. Okay, those are two conditions that need to be fulfilled for us to be able to have a function here, a logarithmic function. All right, so what's the domain? Well, the domain would be from 0 to infinity, not including 0. This is exclusive, not including 0. And the range will be from negative infinity to positive infinity. And let's put some value down here. So at 0, I can, if I plug in a 0 here, log of 0 is undefined, right? Because this is telling me 10 to what power gives me 0. Well, there is no power of 10 that would be equal to 0. So that does not exist, not possible, so we say undefined. If I plug in a 1/2 for my x here, so again, if I'm using the base 10, 10 to what power would give me a 1/2? Well, that's going to be a decimal number, and it will in fact be negative 0.301, and then it keeps going, right? This is an irrational value. 1, so log of 1 tells 10 to what power gives me a 1, and that would be 0, right? And then if I plug in a 10 for x, that would be saying 10 to what power gives me 10. Well, 10 to what power gives me 10, that would be a 1, right? And then I can plug in anything else, and I think I mentioned 100. 10 to what power would give me 100, and that would be 2. Okay, so those are enough points for us to graph that. And so 1, 0 would be right there. 10, 1 would be right here. 100, 2, so we're obviously not going to be able to graph that. And then 1/2 negative 0.3, so 1/2 negative 0.3 would be about here, and then 0 is undefined, so I'm never going to touch my y-axis, and so my graph would look like that. There we go. All right. The x-intercept would be at 1, 0. The y-intercept, well, there is none, right? Because I just said that we are never going to cross the y-axis there. We have a vertical asymptote there, so we're going to say none. And I just said that I have a vertical asymptote, right? So remember, an asymptote is an invisible vertical or a horizontal line that your graph is approaching but never really gets there, right? And that's true for vertical asymptote always. For horizontal asymptote, we have to talk about what they really mean, but vertical asymptote is what I have here, so I'm going to specify vertical, and it is at x equals 0. Is this function even, odd, or neither? Well, there is no symmetry over the y-axis, there is no symmetry over the origin, so this is neither. And the graph is definitely continuous, right? Because if I start at the most left point, I can draw my whole curve in one stroke without raising my pencil. No discontinuity. Maximum or minimum, so we're talking about extrema, and this graph doesn't have any, right? Because this function is going to keep going down toward negative infinity and going up toward positive infinity, so it will never reach a max or a min, so there is no extrema, none. Interval of increase, well, that function, even though remember we talked about how we don't only look at where that is pointing toward, we want to see when I move left to right, what's the direction I'm moving on my curve. So if I start most to the left and I start following the curve, I obviously going to be going up, right? So this function is increasing on all its domain, and so the domain is 0 to infinity. Never decreasing, so there is no interval of decrease, none. In behaviors, I want to talk about my limits. So let's do the right hand side. So as the function is going toward x, as x goes to infinity, right, as I move to the right, this is going to keep going up, very slowly, but it will increase always. So on the right hand side, the limit as x goes to positive infinity of f of x goes to positive infinity. On the left hand side, however, as I'm going left, my function is never going to pass 0, right? X equals 0, we said was my asymptote. So my limit on that end will be the limit as x approaches 0. Well, I'm approaching 0, but from what side? Well, obviously from the right, right? Because from the left there is nothing there. That's no man's land. So I'm approaching 0 from the 0 meaning x equals 0, that asymptote, right? I'm approaching that from the right hand side of f of x. And where is my function going as I'm approaching that asymptote? My function is going down to negative infinity, right? So negative infinity. Okay, that's it for the logarithmic function. Now, we talked about how there is a second logarithmic function, and this will be for your natural log. And really, everything is the same as the log that we just did, but a natural log is just a function with a base e. It's a logarithm, sorry, with a base e. So back to our exponential function. Remember we used f of x is equal to e to the x. The inverse function of this one will be the natural logarithm, okay? And so the domain will be the same as the other log, and the range will be the same as the other log. This is still going to be continuous, no symmetry, and it has no extrema. The asymptote is still going to be a vertical one at x equals 0, same as the other log, right? Interval of increase will still be everywhere on its domain, right? So same as the domain, and never decreases, so no interval of decrease. And the end behaviors are also the same as the other one, as the other log. So as x approaches 0 from the right of f of x, my function is going down to negative infinity, and the limit as x approaches infinity is going to be going to infinity. Now the values are going to be a little bit different because now I have a base e, right? So on the other side, on the other one, I said I used the base 10, right? So I said 10 to what power gives me my x, to kind of decide what my numbers are here, or to explain. Here we will say e to what power, right? So e to what power gives me 0? Well, there is no number there, so again, this is going to be undefined. The 1/2, when I put that in my calculator, I got negative 0.693. 1, so e to what power gives me a 1? That's just like the other one, it's a 0, right? 0. Anything to the 0 power is 1. E to what power gives me 7? That would be a 1 point, oh sorry, that should be a 946. And those are irrational numbers, right? Because those decimals will keep going and non-repeating. And then I'm going to put a 10 here, and my decimal there will be 2.303. And again, this keeps going. The x-intercept is at 1, 0, and there is no y-intercept. Okay, so when I graph that, I'm going to be at 1, 0, just like the other one. My negative 1/2 is going to be somewhere there, negative 0.6, right? At 7, I'm going to be just below 2. So 7, we're going to be just below 2. And that should be enough for me to graph that. Vertical asymptote, so don't touch that axis. And there we go. So essentially the same shape as the other one, right? But this one is just a little flatter, right? You see how it's just a little flatter than the other one, and that's because my base is different, okay? All right. Logistic function. Now, we're not going to really talk about the logistic function much, so I'm going to skip it. If we have time, I told you at the end of the year, if we have time and we're done with everything else, we're going to talk about some logistic functions, but if not, we're going to skip that. Okay. Sine function, we did this one. In class today, but I'm just going to go over it very quickly again. So sine function will be f of x is equal to the sine of x. And remember, I told you that those input for trig functions are angles, right? They're either going to be in degrees or in radian with a pi in it, like 2 pi, pi over 2, etc. But those are angles that we input. The table at negative pi over 2, my sine function is negative 1. And all of that doesn't make much sense yet until we are going to do the unit circle later, right? That will be after Christmas. So for now, just trust me on those values and just write those down. You don't have to memorize those yet. Okay, so here we go. And then I'm going to grab that, right? So at negative pi over 2 as an input, I have a negative 1 as an output, so I'm down here. I'm going through the origin. At pi over 2, I'm going up to 1, so pi over 2 is 1. At pi, I'm back at 0. Then I'm negative 1, back at 0, and here is how it looks. Those are not straight segments, right? You need that curvy feel of that function, right? Those are not line segments. And then make sure at the end that you show that this keeps going with the arrows, right? Arrows just show we're going to keep repeating that pattern forever and ever. This function is definitely odd. If you're looking, quadrant 1 and quadrant 3 are similar, right? And then quadrant 4 is going to be repeating up here in quadrant 2. So there is definitely a symmetry over the origin, which means it's an odd function. And by the way, odd function means the opposite of x are going to be equal to the opposite of the y. This is a continuous function. The domain will be all real numbers, right? This is a pattern that's going to repeat forever and ever. The range, well, my lowest value I'm reaching is -1. My highest one is a 1. So range is -1 to 1. And I'm definitely reaching those values, right? I don't have any holes there, so brackets, right? Including those endpoints. Do I have any local maxima? Well, yes. I will reach that maximum more than once, right? Every time my pattern repeats, I'm going to have another max, max, max. But the y value is the same for all of those, and it's a 1. So local maxima will be y equals 1, and minima will be y equals -1. Remember, when we talk extrema, minimum and maximum, we want to know the y value, because it's the y that tells you how high or how low your function is reaching, right? So those are minimum, maximum are given to you by y values. Now they repeat, and we talk about that later when we do the trig functions. We can kind of skip that for now. I want to add here that this is a periodic function, meaning this has a pattern that repeats. And if you look, if I go here, after that, my pattern will repeat, right? Because I'm back at that point, so I'm going to go up first, down, and then again repeat and repeat, right? So this will be my period there. So the period will be from here to here. That's, oh sorry, not to here, mistake, from here to here. That's the width I need to do one full cycle, right? And then we repeat after that. So one full cycle will be from 0 all the way to 2 pi. So the periodic function with a period of 2 pi, because that's how long it takes from 0 to 2 pi to do one full cycle, okay? Interval of increase, well, okay. So it's going to be increasing from the minimum to the maximum, right? So from here, for example, -pi/2, all the way to pi/2. And then after that, it starts decreasing, right? So I'm going down here, decreases from pi/2, all the way to 3 pi/2, and then it repeats. So how do I talk about those repeats? Well, we're going to say repeats every 2 pi cycle. And for now, I just want to leave that like that for now, right? Later we can talk about more how to write that more specifically, but for now we just leave it there, okay? All right. End behaviors. So an end behavior is one specific value or direction that my graph will settle toward as I'm going toward the infinities on either side. Well, this function never settles anywhere. It's going to keep going up, down, between -1 and 1, -1 and 1, -1 and 1. It never settles, right? This is called an oscillating function. So this oscillates between y equals -1 and y equals 1, right? So therefore, the limit as x approaches either side, either positive or negative infinity of f of x, does not exist. So we say D, capital N, capital E, and that stands for does not exist, meaning there is none. There is no end behavior, no specific value my function will settle at, because it's going to keep going up, down, between -1 and 1 indefinitely. All right, the x-intercept, well, we have a lot of them, right? A whole slew of them. And in fact, the first one is at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and then the other way it will be 0, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, etc. So those x-intercept will be at all the integers. So we're going to say for x equals pi k, where k is an element of the set of all the integers. Okay. The y-intercept, well, there is only one, right? We only cross the y-axis once, that's at the origin, 0, 0. All right, that's for the sine function. Let's go to the cosine. The cosine function is really a sine function that has been, so you're taking your sine function and you're translating it, right? So it's been translated to the side. So cosine function will be f of x equals cosine of x. And again, those inputs here are angles. We want to keep that in mind. And if I want to graph that, so let's fill in my table first. Negative pi over 2 is going to be 0. At 0, the cosine function reaches its max, 1. At pi, I'm going to, okay, so hold on, up here, I don't have a pi over 2 here, so I'm going back down. At pi, I'm going to be at negative 1. At 3 pi over 2, I'm going to be back at 0. And then let's do one more. Let's finish that and say at 2 pi. So we go up, down, down, up, up. So we're going to be back at 1. And that pattern will repeat, right? So watch it again. Remember, those are curves. That's a curvy function, not line segments, right? So don't make those straight lines, right? They're not. You should really see that concavity. Concave down, concave up, concave down again, etc. And again, we don't stop here. We show that this is going to keep going, so we put an arrow at the end. Okay, all right. Domain, well, it will be negative infinity to infinity, right? Because this function is going to keep going in both directions. The range, just like for the sine above, the y value, the lowest one is negative 1, the highest one is 1, so my range is between negative 1 and 1. This function, so my sine function had symmetry over the origin, but the cosine function has symmetry over the y-axis, right? So if I fold on the y-axis, I would have both sides on top of each other, right? So this is actually an even function. And that means that f of x is equal to the opposite of x. So two opposite x's have the same y value. It is a continuous graph. And for the extrema, well, sorry, they're not the same, so I shouldn't do that. The local maxima, I have a lot of them location-wise, but the y value itself is only going to be y equals 1, right? And same for the minimum, y equals negative 1. Interval of increase, well, the function is going to be increasing. Let's go from pi to 2 pi, right? Up, 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 and then it starts going down again, right? And then decreasing, I'm going to talk about 0 from pi, and then repeats. So interval of increase, we're going to say from pi to 2 pi, pi to 2 pi, yes. And the decrease, I'm going to say from 0 to pi. So I have one full cycle in there, right? From 0 to 2 pi. From 0 to 2 pi, that's one full cycle. Then it repeats on either side. So, and then we're going to say repeats every 2 pi cycle. And again, when we do the trig function in more details, we're going to do a better way. We're going to write that in a better notation fashion. But for now, we're good there. In this here, let's talk about how this is also a periodic function. With a period of 2 pi as well. It takes 2 pi to do one full cycle. And behavior, just like the sine function that we said oscillates, therefore there is no end behavior, it's the same for the cosine, right? We're going to say oscillate between, and I'm going to write that a little differently than I did above here, just to show you some notation, right? So it oscillates between y element, meaning my y values are all going to be element of that interval from -1 to 1. Okay, so that's kind of very fancy mathematical notation right there. And then the end behaviors, then we said the limit as x approaches positive or negative infinity, it's the same on both sides, does not exist. D, N, E, capital letters, right? D, N, E does not exist, okay? The x-intercept, well, the x-intercept, so for the sine, it was at pi, and then it repeated for every 1 pi, 2 pi, 3 pi, -1 pi, -2 pi, -3 pi. So we said for every pi integer, right? Actually, you know, this is kind of written backwards, shouldn't have written k pi, right? Because we don't say pi, 2 pi, 3 pi, 4. We say 2 pi, 3 pi, 4 pi, right? So we say the number first. So apology about that. That was kind of backwards there. And so here, I'm not going to have my x-intercept at pi, the first one, but at pi over 2. So I'm going to say it will be at x equals pi over 2. And then it's going to repeat for every, so it repeats every pi after that, so plus k pi. And again, for now, we just write that down. We'll talk about it later when we do trig, where k is an element of all the integers. And the y-intercept is going to be at 0, 1. All right, that's it for the cosine function. This is a video, right? So you can pause me if you need to. Tangent. That's the last trig function we're going to talk about here, because the cotangent, secant, and cosecant are the inverse trig functions, the reciprocal, really, of the main three, sine, cosine, and tangent, and we leave this for our function, our trigonometric function unit. Okay, so the tangent will be f of x is equal to the tangent of x, and just like the other two, that input there is going to be an angle. Then we're going to put some values down here. -pi, we're going to be at 0. At 0, I'm going to be at 0. At pi, we're going to be undefined. Hold on. 0. Oh, no. At pi, I'm going to be at 0 as well. You're going to say, well, is that just a whole bunch of dots at 0? But no. 3 pi over 2, that's where my function is going to be undefined. And then I just picked 7 pi over 4 to have another one, and that would be -1. And I'm not sure why I picked 7 pi over 4. I could have picked just pi over 4, right, and put it at 1, but that's okay. We'll just leave it the way I have it now. All right, so what happens with a tangent is that this is a graph that has a whole bunch of vertical asymptotes. So I'm going to dash them in. Remember, those are vertical lines that are really not part of the function, but are kind of like a limit the function cannot intersect or pass over, right? So there, it's like a blueprint for my function. Okay? And then the function itself is going to, so from the bottom, I'm going to come up toward my 0 there. And it's curvy, right? I have that concavity. And then switching concavity, I'm going to go up to infinity. And they're all the same. So concave down on the left, and then concave up on the right. Concave down, and then concave up. Okay? So that's your tangent graph. And if you notice, the domain is going to be broken, right? Every time I have an asymptote, I'm going to have to exclude that number from the domain. So we're going to make it as simple as possible here. We're going to say from negative infinity to infinity, right? Because that function is going to keep going on either side, except x equals, and we're going to say pi over 2 plus k pi. And then again, we're going to say k is going to be an element of the set of all the integers, okay? So pi over 2 is my first one. And then my next vertical asymptote will be at pi over 2 plus pi. Well, pi over 2 plus pi is 3 pi over 2. Plus another pi. And then subtract pi, right? Because that width here every time is the width of pi. So subtract pi on either side and add pi. So plus or minus pi. And the minus is going to be taken care of with the integers that are negative values, right? That will take care of that minus there. The range, on the other hand, has no restrictions, right? It's going to keep going down, keep going up, all real numbers for the range. So the range is all real numbers. Okay? This is not continuous, obviously, right? Because we have all of those vertical asymptotes. But this is definitely an odd function. If you're looking, we have that symmetry over the origin, right? So this is going to be an odd function, meaning the opposite x are going to be equal to the opposite y. The asymptotes are going to be vertical as opposed to horizontal, right? And they're going to be at x equals pi over 2. So remember what we said here, for the restriction on the domain, those x values are not part of the domain because that's where I have a vertical asymptote. So that's exactly where my vertical asymptotes are, right? So we just recopy that from up here. So at x equals pi over 2 plus k pi, okay? I want to say here somewhere that this is a periodic function. And that the period, so this one, as opposed to sine and cosine that repeated every 2 pi, this one only takes 1 pi to repeat, right? We have a vertical asymptote every k pi. So the period, it's a periodic function with a period of pi, as opposed to 2 pi for the other two trig functions we looked at. We do not have any extrema because this graph is going to keep going down toward infinity and up, right? The range, remember we said, is all real numbers, so no extrema. Both of them, none. Interval of increase, well, that function always increases from left to right. You're always going to go up. No matter which branch you pick, when you go from left to right, you're going to follow the curve, moving upwards. So this is increasing on its domain. That's one way of saying it, once you mention the domain, right? So that would just be recopying that domain here, or once you mention the domain, you can just say on its domain. Interval of decrease, we have none, never decreases. And behaviors, well, just like the sine and the cosine, this is a periodic function. It's going to repeat over and over and over, never settling for any y value specifically. So the limit as x goes to infinity, oops, I should put plus or minus because I said on both sides it's going to be the same. So the limit as x goes to positive or negative infinity of my function does not exist. D, N, E. The x-intercept, well, I have a whole slew of them again, right? Infinitely many. The first one is at 0, then pi, then 2 pi, etc. So that will be every pi. So at x equals k pi. And we already said up here that k stands for every integer, so I don't need to re-mention it here. And then my y-intercept will be the origin, 0, 0. All right, that's it for the tangent, I think. Cotangent we skip for now. Secant and cosecant, those are reciprocal of the other trig functions, so we're going to skip. And then I think Did I not have one special one that I wanted to talk to you about? Actually, two. I have two special ones. So let's just do the f of x is equal to 1 over x squared. And that's almost like a reciprocal function, except instead of just having an x here, we're going to have an x squared. And that's going to change our graph a little bit. And so I'm going to go ahead and do a table of value. So if I plug in a negative 2 would be a negative 2 squared is 4, so 1 over 4. If I plug in a negative 1, negative 1 squared is 1, and so 1 over 1 is just a 1. If I plug in 0, can I put in a 0 in the denominator? Absolutely not, so that's undefined. So now you already know we have an asymptote there, right? Somewhere we have an asymptote. And then I'm going to go to x equals positive 1. Well, if you plug in a 1, 1 squared is 1, 1 over 1 is a 1. If I plug in a 2, 2 squared is 4, so that'll be a 1/4. Okay, so let's graph that. So negative 2, we're going to be at 1/4. It's kind of hard to graph there. At negative 1, you're going to be at 1. 0 is undefined. At 1, I'm going to be at 1. At 2, I'm going to be at 1/4. And then really, I'm going to show you, we're going to have an asymptote at 0, because remember we said that's undefined right there at 0, right? So I'm going to go ahead and do my little dashed vertical asymptote, which I know is not part of my function, but I just want to use it so I know where to not go with my graph. And then I'm going to hug that asymptote going through those 2 points I just drew. And I'm going to come very, very close to my x-axis, but never really touch it. And you do the same on the other side. And you're going to come very, very close to that x-axis, but never really touch it. Okay. You're never going to go below the x-axis, because that will be where the y values are negative. Well, you can't get a negative out of a number that's squared, right? Whatever x value you're going to plug into your function here, you're squaring it. So that's always going to be positive. So the y's are always going to be positive. You're never going to be down there, okay? Domain, well, the domain will be from negative infinity to 0. Do not include 0. Jump over it. So union or 0 to infinity. The range, well, what's my lowest value I'm going toward to? That will be y equals 0, but I am not going there. I'm not including it, so I need a parentheses, and then up to infinity, right? No restrictions there. This function is obviously discontinuous because I have my vertical asymptote in the middle, so let's put that asymptote down. It's a vertical one, and it is at x equals 0. The function is even, right? Because if I would fold on the y-axis, well, I would have those two branches on top of each other. So this is an even function, meaning the x, the two opposite x's are going to give me the same y values. There is no maximum and there is no minimum. You're going to say, well, there is a minimum, 0, but no, not really, because we're never really going to touch it, right? We're approaching it, but we're never really getting there, so we're going to say none. You only have a minimum or a maximum if you're actually going to that y value. Well, 0, look, on the range we said is not included, right? So we're never going to 0. We're going towards, but never there, okay? Interval of increase. Well, look, I'm going from left to right. My function is going up, 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 right? And then jump over the asymptote, and then suddenly we're going down, 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 right? So the interval of increase will be that left branch, which is this one right there, right? So from negative infinity to 0. And then the decrease will be this right side of the graph, so that will be from 0 to infinity. End behaviors, well, end behaviors, remember, is when we're approaching the infinity. So as my graph keeps going toward negative infinity, it's approaching 0. And as my graph approaches positive infinity in the x values, my y's will also approach 0. So they're both the same, so I write it as one single limit. As x approaches positive or negative infinity of f of x, my function is going to be approaching 0, equals 0. We're almost done, aren't we? I need an x-intercept. Well, we said we're never going to touch the x-axis, right? So none. And the y-intercept, we have an asymptote there, so surely we know there is not going to be a y-intercept. All right. I think that's enough for this function, for this video. So I'm going to stop here, and that's all you need really to be ready for our quiz anyway. I'll see you in class.